Hey kids! It's time to talk about KMT, that is kinetic molecular theory and properties of gases. Hashtag, we know hashtags are no longer cool.
But we're going to do it anyway.
Hashtag awesome. All right, let's go then. So what we got here, this should look very familiar from Unit 1, all the way back to Unit 1. These are gas, liquid, and solid particles. Now, can you tell me what you remember about that stuff?
I remember that gases are compressible because the particles are far apart, moving fast. Solids are most dense, close together. Solid particles are packed, so they vibrate in motion. They're not stuck. They vibrate a little bit.
Okay.
Liquids flow. They can move past each other. What else do we need them to remember?
That's pretty much it. All the particles of each state of matter are in constant motion, but obviously gas particles move the fastest.
Yep, and that's what we're going to talk about now.
So yeah, let's good segue into gases. Love it.
KMT.
KMT, kinetic molecular theory. Let's talk about it. Postulate number 1, linear motion. So that means that all gas particles exhibit linear, which is straight line.
So not this.
Not this, not waves. Straight line motion, which is constant and random. That's pretty much it for linear motion. Another postulate is elastic collisions. When gas particles collide with each other and their container, the collisions involve no loss of energy. Now, what else can you think of that is elastic?
Bouncy ball.
Bouncy balls is a wonderful example. So in the real world, though, when you drop a bouncy ball or something, there's a little bit of loss of energy. But when we're talking gas particles, imagine it's a bouncy ball that doesn't lose energy when it bounces off stuff.
So comes in, bounces back, still straight line.
Still has the same amount of energy.
Okay.
Super bouncy ball. That sounds like fun. Okay. Intermolecular forces, the forces between molecules. These are our attractive forces. The attractive forces between gas particles are so small they are assumed to be zero or negligible. And that's really because gas particles are just moving way too fast.
Yeah, they don't have time for that.
Nobody got time for that, right? Finally, we have gas volume. Now, the volume of a single gas particle is so tiny that it is said to be zero. Now, of course, if you have a whole bunch of gas particles together, yes, we have volume, but we're talking about a single gas particle, just one, so small, said to be zero. Those are our kinetic molecular theory postulates, and that kind of governs how we talk about just gases in general.
So the 4, to recap, we have linear motion, elastic collisions, no intermolecular forces, and no volume for one particle.
That's essentially it right there. So that's something that you really should think about when you are working through some of these properties and just thinking about gases in general, because we know you will. All right. So let's talk about the 3 properties of gases.
Okay. Temperature, volume, and pressure.
Temperature is first.
Okay.
So temperature is basically not how hot or cold something is.
How much energy it has.
How much energy it has. The average kinetic energy of gas particles tell you how high or low the temperature will be. So what does it mean? What's kinetic energy mean?
Kinetic energy is energy of motion. Potential is stored. Kinetic is motion. You'll learn all this in physics.
Right. So if something is moving very fast, its temperature is very high.
Yep.
So you can actually measure this with an equation. Ke, kinetic energy, is equal to 1/2 times the mass of a particle times the square of its velocity. And this is also on your formula chart. You don't have to commit it to memory right now. But that's just, I want you to, temperature is not how hot or cold something is. It's how fast the particles are moving.
Okay.
All right. So let's get out of here. The next property is volume.
Okay. Now this is particles, not one particle.
Yes, these are many gas particles. They do occupy a certain volume, a certain space. So if this room that we're in is one container, it does have a certain volume of gas particles. Now, something that is smaller, say a Coke bottle, will have a smaller number of particles in it, assuming the same pressure and temperature, of course. And so the volume will be smaller.
Okay.
Should be fairly easy to understand. And then finally, we have pressure. Now, pressure is the force applied over a certain area by gas particles when they smash into the walls of their container. And we can actually measure that by saying the pressure is equal to the force applied to a certain area. So obviously, if you increase the force and the area stays the same, the pressure is going to be higher.
Mm-hmm.
If you increase the area and the force stays the same, the pressure will be lower.
Right.
So one example that I always think about, it's not really with gases, but it's with snowshoes. People put those tennis racket looking things on the bottom of their shoes, and that's how they walk through the snow. It's because they're trying to increase the surface area that they come into contact with the snow, applying the same force because they're still walking, and that actually puts less pressure on the snow so they don't fall through. And so that's very much, the best example I can think of. Can you think of any other ones?
Well, what if I have a certain force when I punch or hit, right?
Okay.
If I hit you with a closed fist, I'm not going to hit you.
Okay.
If I hit you with a closed fist, I have a small surface area. If I hit you with an open hand, more surface area, it's going to hurt less pressure.
Okay, so the bigger surface area is better. Slapping hurts though, and
Let's
so
not do that.
and so does punching. I don't really want you to punch me or slap me. Sorry, she's not going to hit me. But that is very, very good point. So that is pressure, and that applies to gas particles as well. I think we're good here.
Yeah, I think we're done.
Thanks.